This time I'm going to explain the air conditioning system and probably go into floor heat and whatever else is associated, temp control. So to start, the schematic's drawn as if we have bleed air on the aircraft already, but from the engines we'll end up with bleed air making its way through or to the cross-ship manifold here. And it'll be standing by until we turn the system on. Now over here on the left hand side, these tap-offs that allow bleed air to make it to these locations, and I'll explain them. That tap-off right there, and that tap-off. Now this one that I'm going to right now controls our cooling air exit door. And then this other one, this one right here, controls our fan. Based on signals from the AMSC that'll get sent to these torque motors, these two torque motors, it will change the amount of bleed air that is going to the torque motor, which in the case for the exit door, it'll open the exit door, modulate it in flight. When you're on the ground, I kind of drew the criteria over here, 0.3 Mach, legs extended on the ground, then the cooling door will be full open. And then this bottom torque motor will modulate the amount of bleed air that will go to our cooling fan, which is kind of depicted up here. And the cooling fan will turn, sucking in air through the ram inlet, and then it'll blow it across our primary heat exchanger right here and our secondary heat exchanger right here, basically cooling the air that's going into those heat exchangers, the primary and kind of secondary cooling stages. Alright, back to the flow control valve. So the flow control valve, if you have it in normal, we have bleed air coming from the cross-ship manifold, it will open up, and we've got kind of a Y where bleed air can go. So we'll just follow it this way since it's going to be standing by over here. So it'll overcome that check valve, come up here, and we'll end up with hot bleed air in this area here. So these valves, they're drawn open right now, but bleed air will stand by there to kind of do some work later, and I'll explain that. And the other tap off will make its way over here and go to our first stage of cooling, our primary heat exchanger. In this first stage, we have two sensors, but one of them's an overheat thermostat and the other one is a temp sensor. And so the 160 here, the whole purpose of that is so the AMSC gets its signal from the sensor, and then because it's always trying to maintain the output of the primary heat exchanger at 160, the AMSC will then modulate our cooling air exit door in order to try to keep it at that 160. The 277 comes into play because if the temperature rises to 277, at that point the AMSC opens our cooling air exit door fully and it gets locked into place. Alright, so from the primary heat exchanger passes both of those sensors, and we have a tap off here where this partially cooled air is going to come down. It's going to overcome this check valve, and it's going to be sitting here at our low limit temp control valve waiting for it to open or close depending on what the AMSC tells it to do, and I'll explain that in a second. Going back to this other tap off, it's going to hit our air cycle machine, the compression side of it, and this is where our partially cooled air is going to be compressed. And when you compress something, or you compress air, it gets hotter. And so our other temp sensor up here, our high limit, it's looking for a temperature of 547 degrees. If it reaches that temperature, the 547, then the signal that's sent to the AMSC will then close our flow control valve, preventing bleed air from coming into the system and overheating our ducting. So our compressed air at this point will make its way through and make it to the secondary heat exchanger, where it's further cooled. It'll come up and around through ducting, overcome a check valve, and then it'll hit the rapid expansion portion of our air cycle machine. And what that does is, as it rapidly expands the air, it supercools the air and it removes the moisture, so you end up with some very moist air at this portion of the air cycle machine. And so the next thing it's going to hit is an area where it's going to hit water separator sock. And the purpose of the water separator sock is to separate the moisture from the air. Now, because there's so much moisture in there, it has a tendency to freeze up. And so the partially cooled bleed air down here that I was talking to you about, it'll make its way up here based on the AMSC's input signals to that torque motor, and it'll mix in with the supercooled air, and what they're trying to do is maintain a temperature just above freezing, so 37 degrees at the outlet of the water separator. That way the water separator sock does not freeze up. It just separates the moisture and then vents the water outboard, or overboard I should say. In case I didn't mention it, that's this sensor right down here that sends the signal to the AMSC to try to keep it at that 37 degrees. So then we'll end up with cold air making its way across here, and then it starts making its way into our ducting. So you can see here, it'll make its way up here and into the various ducts within the the troop compartment, the courier compartment, and the flight deck. Now, as it makes its way up and through, you'll notice that there's some sensors down here. So one of them's an anticipator thermostat, and the other one's an overheat. The anticipator is set for 290, and then the overheat thermostat in here is set for 330. Now the way this system works is, if we have cold air coming into here, into this duct, and we wanted to increase the temperature, then by increasing the temperature up in the flight engineer station, that's going to tell the AMSC that we want, approximately 80 degrees in the flight deck for whatever reason. Then at that point, the AMSC will start cracking open. I'm going to choose a different color, that way you can kind of see it better. The AMSC will start cracking open the temp control valve to add hot bleed air into the ducting, up and into, which will make its way out to the various compartments, or flight deck. Let me see, what's this one? Troop compartment. So this one will make its way up into the troop compartment. Now, if the duct temperature, like I said, it's an anticipator also, so it anticipates with the AMSC when the duct temperature is approaching the selected temperature. So if we did have 80 degrees, 90 degrees, once it starts seeing that, it'll send the signal to the AMSC, and the AMSC will then start anticipating that the temperature in that compartment will reach there, so it'll start cracking close the temp control valve. That way there aren't any overshoots within the various compartments. Let's see, now the overheat thermostat here, what that does, if the temperature within the duct reaches 330 degrees Fahrenheit, then it will completely close the temp control valve, preventing or attempting to prevent a duct overheat. And the same works over here in these ducts with the temp control valve. Depending on the setting you have, the temp control valve will open to allow bleed air to mix with the cooled air and warm the various compartments. Let's see, making its way there, up and through. So this one over here is going to be the flight deck, and then let's see, this is going to be kind of the relief crew compartment. Alright, and then you will also end up with air making its way over here, overcoming the check valve, and mixing into this plenum here. For the sake of trying to keep this as short as possible, the cargo compartment works identical to the flight deck. And so I'm going to start at the air cycle machine, which the output of the water separator, once again, is going to make its way through here and into this plenum. And right here is our temp control valve. And as it mixes in this plenum, it'll all make its way down to the various outlet ducts in the cargo compartment. You can see just following them around. Alright, I deleted everything just to try to make it a little easier to see now. So now that we've talked about the general how the system works, so I'm going to talk about the integrated mode first. So integrated mode is going to work by the air that's coming out of the water separator is going to hit that thermostat. And so in auto, we can have up here in each compartment. So in the flight deck, let's say the engineer has it set to where it's going to be about 70 degrees up in the flight deck. And then in the courier compartment, the setting up here, I have it to 80. And then over here in the troop, we have 90 for whatever reason. Okay, so what's going to end up happening is the lowest setting that you have set up there, so this one's going to end up being 70 degrees. The AMSC is going to work to regulate our low limit temp control valve to put enough air into just prior to the water separator so that the air exiting the water separator is going to be at 70 degrees. And what that does is as the air comes out and makes its way through and gets to the temp control valve areas, the temp control valves don't have to open as much to apply that bleed air into the ducting in order to warm the air up at that point. So the air that's going to end up going up into the flight deck, out into this ducting, it's going to be 70 degrees. So the temp control valve for that is essentially going to be closed. It's not even going to be used. Then for the courier compartment, it's going to open just slightly in order to get mixed into the 70 degree air to make it to 80 degrees, and the same is going to be true with the troop compartment. This temp control valve is going to open just enough so that the air going into the troop compartment is going to be about 90 degrees. Alright. So in the manual mode, which is slightly different, the air coming out of our water separator is going to be 37 degrees. Right there. So the low limit temp control valve with inputs from the AMSC is going to input just enough air to keep the output of the water separator at 37 degrees. And so what this does is, as air is making its way through, in manual mode, you no longer have it automatically trying to keep the temperature at a certain degree. At that point, you in the flight deck, you're going to end up moving the switches to make it a little more hot and a little less hot up in the flight deck. And that directly will move these temp control valves to open slightly, open more, close, in order to get the temperature right where you want it. Alright, lastly, go into some underfloor heat. So we had bleed air in our cross-ship manifold over here. Now, bleed air will also make its way down this ducting through our priority valve, and it will allow bleed air to make its way through here to our underfloor ducting. Alright, let's see. Now this is our floor heat temp control valve, and so we'll end up with hot bleed air just kind of sitting here waiting. And if you notice, we've got these fans right here that are sucking in air from the cargo compartment. There's some grates down there, and it'll bring in air from the cargo compartment down to the underfloor area. And what that ends up doing is, as it's sucking in air from the cargo compartment with the fans, then our floor heat temp control valve will open or modulate to mix in with the air coming in from the cargo compartment, and it's trying to maintain a temperature of 75 degrees in the underfloor area. Now we've got a temperature sensor that's set at 230 degrees, and we've got an overheat sensor that is set at 330. So if the temperature in the underfloor reaches that 230, a signal will be sent to the AMSC, and the AMSC will then drive our floor heat temp control valve closed. Now the overheat sensor, if it were to reach 330, the same thing will happen, is power will be removed from the temp control valve and it'll close. You will also get a duct overheat, in which case it'll be considered a center duct overheat, and we will end up with our valves closing here, and so we end up losing our floor heat temp control valves, our APU ISOs close, our APU bleeds close, and our left and right ISOs close, isolating any bleed air from coming down to this area. Erase it all here. And I know I only talked about the left-hand side, or I shouldn't say left-hand side, but the forward floor heat, but it's the exact same in the way that it works for the aft floor heat. They've got the same limitations and sensors.